So we have the slope of the temperature profile in the preheat zone leading up to the reaction zone is given by a rho u Cp Ti minus T naught divided by K. Let us keep in mind that we are actually hunting for u. This is what actually we do not know, and this is what we are actually looking for, and we are hoping that we will be able to actually get this when we try to use the interface matching condition between the two zones. So what we have to do next is of course integrate the second equation and then also get a slope from there, evaluate it at x equal to 0 plus, and then equate these two, and therefore we expect to get the u. That's how we are going to go about this. That's what's looking down the pipeline we are going to be doing. But at this stage we now have a problem. The problem is that we suppose that we have T equals Ti in both the boundary conditions leading up to x equals 0 minus on the one side and x equals 0 plus on the other side, but we do know what it is. All we are basically saying is the temperature has to match, and we have to now plug in a value of the temperature Ti over here, and we do not know what it is. So how the question basically is, how do you deal with the situation of not knowing the temperature, right? So there are a couple of tricks about this we will talk about. In both the cases we try to now replace this temperature by a known temperature without incurring too much error. So the bottom line basically is without incurring too much error. So what we are going to do from this side, looking from the preheat zone towards the reaction zone at the interface between these two zones, is to now say that this is equal to rho u, approximately rho u Cp Tf minus T naught divided by K. Why would you do this? Well, basically the temperatures that we are actually given are Tf and T naught. Ti is an unknown, and we are not really making any bones about trying to find that out in the first place. We are trying to actually see if we can replace the unknown by something that's known without incurring too much error. So the last part, without incurring too much error, is where the crux is. So let us look at how Tf departs from Ti. So the answer is, if you now look at the preheat zone and the reaction zone, basically you are having the temperature Ti very close to Tf. The only difference between these two is the temperature climbs up a little bit more within the reaction zone to level off at a constant slope at the end of the flame thickness. Alright, so you could say that you're almost there, except that the slope is not 0. Alright, so you have a finite slope, a finite non-zero slope that we are trying to look at, but the value is pretty small. Well, if you want to be a little bit more careful about this picture, we got to keep in mind that the preheat zone solution is going to actually give you a exponentially increasing solution, is what you are looking at. So effectively we are talking about a value Ti that's here, and the preheat zone solution would go like this, and the reaction zone solution would go like that, right? So that's what we are looking at. So Ti, the point here we have to keep in mind is this is T naught. So relative to T naught, so look at this difference, or this difference relative to T naught, Ti is as close to Tf. It's not as if like Ti is generally close to Tf. The question is how close is, it's quite close relative to T naught. That is, like we are kind of looking from here and then seeing that those two temperatures are very close to each other, right? So that is the trick that we are playing in the preheat zone, and I'll show you how to play the trick in the reaction zone where we don't know Ti, and we will be integrating in this region, and if you aren't anticipating the kind of trick that you are going to play, you must be having your eyebrows raised at this stage. How on earth am I going to have Ti be replaced by T naught, okay, because that's what I need to do, okay, because I'll be in this region. I'm going to go from Ti to Tf, and T and T naught and Tf are what's given. Ti is unknown, so in this case I am replacing Ti by Tf. In that case I will have to actually replace Ti by T naught. Whew, can I ever do that? We'll see how it works, huh? So wait with bated breath on how we are going to play that trick. So let's just go ahead with so we now have this, so we'll just go ahead with the second equation to integrate it once. So the way we want to do that is considering to rewrite it is it as 2 dt by dx times 2, which is like, if you now multiply this equation by twice of dt by dx all the way through, then it's possible for us to now write this as d by dx of dt by dx the whole squared equal to negative 2 dt by dx w q divided by k, right. If you want to just check, we can see that if you now differentiate this, you get a 2 dt by dx d squared t by dx squared. So and then the 2 dt by dx gets cancelled on either side. So if you now do this, the reason is we can now have exact integrals on both sides. So integrating once, right, from 0 plus to infinity, along x, okay, along x, we get dt by dx the whole squared evaluated at x equals plus infinity minus dt by dx the whole squared evaluated at x equals 0 plus equal to, you're going to have this integrated from 0 plus to infinity minus 2 dt by dx wq divided by k times dx. So you could actually say this is not really an integral with respect to x anymore, it's an integral with respect to t, okay. So again, you don't have to worry about, and then of course what you have to do is you have to now realize that the limits of the integral have to be substituted in terms of temperature instead of the x location value. Therefore we can write this as minus integral ti to tf 2q w divided by k dt. Now just in case you are one of those people who is impatient about what's going to be the outcome and what is it that we are gaining out of this, I don't know if you remember, I told you that the biggest difference that we are going to get between what we are doing with all these equations rigorously or seemingly rigorously in a mathematical sense when compared to the phenomenological energy balance that we did earlier on is we got all the dependencies right. The only thing that we are going to gain is a square root of 2, okay. So the factor square root of 2 which is different from the phenomenological expression. Square root of 2 is 1.414, so you are about 41% off in the phenomenological analysis. That is still within the order of magnitude, you see. So 1.4 is about of the order of 1. So that was an order of magnitude estimate. So for an order of magnitude estimate, that was a pretty good job. So question is, where are we getting the square root of 2? The answer is we are actually having this 2 showing up here, right, because we now multiplied by 2 dt by dx, and then keep in mind that this is going to be a square and I'm going to equate this to this, right. So if I'm going to have to equate this to this, then I have to take a square root. So I get the square root of 2 coming from right here at this particular step, okay. So now notice that this is going to be 0, because you're having your dt by dx go to 0 at x, as x tends to infinity. I also want you to point out that we are actually having the x go from here, that is the origin, and this is very important for us to think about as engineers. X equals minus infinity as far as the preheat zone is here, whereas x equals plus infinity as far as the reaction zone is here. Okay, so this doesn't look like very far away when compared to that. It's not like we are talking about minus infinity is being here and plus infinity being there and so on. No, that's not what we are really bothered about. Okay, so infinity is something that's very kind of flexible. It's very contextual, right? So the reason why we are saying this is actually going to be a very small infinity when compared to that is because you see that you're going to have a steep variation in the reaction rate within this region. It's going to rise and fall within the small region, and then you have to now take very small steps to capture that steep rise and steep fall. Okay, so that means to say we are ultimately trying to actually integrate this w with respect to t, and you have to get an area under the curve of w as it rises, as the temperature changes only a little bit between Ti and Tf. Okay, and that rise and fall needs to be done over very small steps, and if you now keep taking very small steps, you pretty much reach you get tired, and then you say, well, I think I have reached infinity, if you haven't, even if you haven't gone too far. Okay, so that's essentially asymptotics for you. So this is what is called as a inner zone, this is what's called as an outer zone. This zone has a different length scale when compared to that. Okay, so we are what we mean by length scale is a characteristic dimension over which we would march. So that's exactly what we are talking about when we are now saying that this is actually going to 0 there. So which means we now say dt by dx the whole squared x equals 0 plus is equal to integral Ti to Tf 2q w divided by K dt. So Q is the heating value, K is the thermal conductivity, those are like properties of this system. So W is the one that's actually varying with temperature. Okay, and so this integral essentially is of W with respect to temperature. Keep that in mind. So let's call this B versus let's call that capital A. And we now want to actually equate A and B, except A is actually the derivative at x equals 0 minus, whereas this is B is actually square of the derivative at x equals plus, so we have to equate this with square of that. Okay, so A squared equals B implies we now say rho u the whole squared Cp squared. See how I am actually squaring things. The rho u actually would indicate the mass flux, so you want to just keep it together. Cp squared Tf minus T naught the whole squared divided by K squared equal to 2q divided by K integral Ti to Tf. As a matter of fact, we should have thought about trying to get rid of Ti in favor of T naught right here, because we did that when we were trying to get A. While getting B, we should actually try to get rid of Ti. We will do that in a minute. Okay, so that's what we should be looking at. But now the cat's out of the bag. We will now try to figure out if that it's not going to be very difficult for us to replace Ti by T naught without much error. So that's something that I'm going to show you or talk about pretty soon. So here we go, how to simplify this a bit further. So rho u the whole squared equals 2k q divided by Cp Tf minus T naught integral Ti divided to Tf W dt. Now note that Q equals Cp Tf minus T naught, right, or this is actually the adiabatic energy balance. So this was the heat released in the chemical reaction, which is essentially the difference, the negative of the difference in the summation of standard heats of formation of products to the standard heats of formation of the reactants, and this is actually the sensible enthalpy rise of the mixture between initial and final temperatures, right. And in fact to be able to notice this, made a mistake I guess. So we have a Cp squared Tf minus T naught the whole squared. So it is mainly to actually cancel this off that we tried to replace Ti by Tf in a hurry back then. Okay, so you might think both ways. If you got rid of Ti there, you should have got rid of Ti here. But if you didn't get rid of Ti here, why did you get rid of Ti there? Okay, so we wanted to get rid of Ti there because we want to cancel this, and we could still go on with this. Okay, so let's keep going on and see where we want to make a change. So therefore rho u squared equals, we'll now for the first time introduce this notation rho naught SL squared. This is basically notation. We could basically say rho u is a constant in one dimensional steady state, right. So rho u is the same as rho naught u naught. Okay, rho u is also equal to rho infinity u infinity. Alright, so the reason why we are saying so many things is the way we want to actually look at this as the laminar flame speed. Okay, SL stands for the laminar flame speed. Okay, is always relative to, I shouldn't say always, but we have to specify this, the laminar flame speed is relative to the unburnt reactants. Okay, when you now say rho naught SL, that means the laminar flame speed is relative to the unburnt reactants. That means to say you now have a flame that is propagating into the reactants, and the question is, you could be actually sitting on the flame and getting the reactants to come into you at the same speed, or the other thing that you can think about is you now have the flame that is propagating, and then the products are actually flowing out, you see. Now if you are actually looking at the flame speed relative to the products, you will get a different speed when compared to if you are looking at the flame speed with respect to the reactants, because the reactants and the products are having different speeds themselves. Therefore it's always quite important for us to note what the flame speed we are talking about, and usually we are talking about a flame speed with respect to unburnt still reactants. Alright, but rho u is a constant, so a less controversial term is what's called as the mass burning velocity. Okay, so mass burning velocity or mass burning flux, if you can call it different ways, laminar mass burning flux is essentially rho u, and it didn't matter whether you are actually talking about it with respect to unburnt mixture, reactant mixture, or the burnt products, because it's going to be rho u is going to constant, you see. So when you're talking about a flame speed, then it has to be specified that we are talking about it with respect to unburnt reactants. So there we are. So you could now write this as 2k divided by Cp Tf minus T naught integral Ti to Tf W dt, and we are now going to say, so SL is equal to 1 over rho naught K over Cp, or 2k over Cp, 1 over Tf minus T naught integral Ti to T naught W dt. Now could approximate I am saying could, I am not saying should. Okay, we could approximate integral Ti to Tf w dt as integral T naught to Tf w dt without much error, because this is an integral, and what we are talking about is, if you now look at how the w goes, right, we are looking at essentially the area under this curve. Well, not exactly this curve, this would be w dx, we are looking at w dt, this is w with respect to this temperature variation, right, and you can easily see that the w is actually 0 outside this region. So you might as well actually start integrating from any temperature upstream, you won't really care. Okay, there is hardly going to be any contribution of w there. Okay, so therefore it's because it's showing up within the integral, then it's possible for us to actually replace Ti by T naught. Otherwise it would have been much harder in this kind of situation, like algebraic, that would be much harder. There is no way you can justify that, but this is reasonable, this is pretty good. Why would you want to do this? You don't have to do this, as I will show you soon, but why would you want to do this? What would we get out of seeing this? You see that 2k divided by Cp 1 over Tf minus T naught integral T naught to Tf w dt. What do we have? This is in fact very similar to the first expression that we obtained phenomenologically, except for two things. One, the square root of 2 factor that I have been saying we will get, and we are right there getting it. Starting from this point onwards we get this 2 there, and then of course it's a square, therefore you get a square root of 2 in the final answer. The next is a little bit more important, which is originally we simply said we had SL equals 1 over rho naught integral 2 kW divided by, sorry, didn't have the 2, kW divided by Cp, and the question was what was the W. If you simply had a kW by Cp, then we assumed that the W was actually prevalent over the entire flame thickness delta, and as if it was a constant, alright, but that is not really the case. The W varies significantly within this distance. In fact it is actually lying very low up until the reaction zone, and then starkly increases and then decreases within a very narrow region called the reaction zone. So the major effect of the rigorous mathematical exercise is to recognize that W varies within the reaction zone and take its variation as it is. So we are not really plugging in a W that is a constant, and then the question that we had was what would be the constant, and we now came up with this combination called W naught infinity, right, where W naught infinity refers to evaluating the W, the reaction rate with reactant concentrations for upstream and the flame temperature downstream, right, that is what naught infinity was referring to, and that would actually give you the highest value that was possible. Whereas if you now have an integral like this, what does this look like? The reason why we wanted to substitute for Ti as T naught in this integral was to actually see what this looks like. This is now beginning to look like more of an average, you see. So this is an average reaction rate between the two temperatures, the limit temperatures, T naught for the reactants and Tf for the products. So if it is possible for us to actually take an average reaction rate, then whatever we got previously with a square root of factor 2 thrown in is what the rigorous analysis gives us based on the Schwab-Zeldovich formulation, right. Okay, so can we do a little bit better? Is it possible for us to not necessarily make this approximation, okay, and then we just plot on saying that let me actually see how this Ti kind of thing is going to work out. Okay.
That under root, the limits of integral is Ti to Tf. The
Up here?
Yes, sir.
Thanks. When you have too many t's, this is what happens. Huh? We want to see if we can evaluate this integral. That means we now have to explicitly take into account the dependence of W on temperature. And what is that dependence? That dependence is essentially given by the Arrhenius law, where we are now saying W is now going to be A e to the minus capital E over RUT times concentrations of the reactants. Okay. Now keep in mind that the concentrations of the reactants are actually going to fall like this, and the A e to the minus E by RT times the concentrations is now going to give rise to a certain variation with temperature, which is a bit peculiar. So as a simplification, we want to bother only about variation with respect to temperature, which means we will as a first step we will now say for a zeroth order reaction, W equals A e to the minus E over RUT, and that's it. Of course all along we have been using W instead of omega. Omega is the number of moles per unit time per unit volume. Okay, that's how the reaction rate is going to be, whereas W is actually the number of kilograms per unit time per unit volume. And therefore the difference is you now have to have a molecular weight thrown in here, but we suppose that A contains that as well. So let's not worry about that explicitly, but whenever you are using W or omega or any of these things, you have to be very careful about the units. Okay, and this is many times where you get into troubles with numerical calculations. So keep this in mind. We are still working on a mass basis, and this is all we are going to have for a zeroth order reaction. That means we are not going to worry about how the concentration varies along. Alright, which means what are we actually looking for? Since we have done the phenomenological expressions, right, we have some physical intuition about what to expect. If you are going to do only the zeroth order reaction, not worry about the reactant concentration decrease into the reaction zone, then all we are basically looking for is this is going to look like the average is the peak value W naught infinity divided by beta. That's the correction that we are basically aiming for. Okay, so is it possible for us to actually show that this average reaction rate is going to be like W naught infinity divided by beta? That's what we did before when we said if we wanted to keep in mind the variation of W with respect to the flame thickness, and say that it varying mainly within this small region, and therefore we scale this distance by as delta divided by beta. That's what we did. Okay, then we got SL equals 1 over rho naught integral K W naught infinity divided by beta Cp. So essentially we are looking for this average integral. If you evaluate it as it is without replacing Ti by T naught, is it possible for us to show that this will be somewhat like W naught infinity divided by beta, is what we are basically looking for. We are not looking for further corrections which are taking into account the reactant concentration decrease into the reaction zone, and still further corrections with non-unity Lewis numbers, which we did before. Okay, because those things are still not possible with what we are doing now. Okay, so now in this case see that E over RUT TF, particularly TF, is typically a large value, which is around 10, which means it's 1 order magnitude more than unity. Keep this in mind because most hydrocarbon fuels you have E's of the order of 30 to 140 kilocalories per mole. That's again a mixture of units. You're not talking about joules per kg, it's calories per mole there. So you have to make that conversion. This is typically how the values are given, and TF is anywhere between 1500 to 2000 Kelvin or even upwards, and RU is equal to 1.98 calorie per mole Kelvin, right. So if you now take these values, you will find that this is of the order of 10, which is quite larger than 1, and we are going to use that fact. So what we want to do is, if I equal to integral Ti to Tf W dt, right, then this is equal to Ti to Tf A e to the minus E over RUT dt. What we want to do is, we want to basically be looking at a variation in temperature only within the small region, right. That small variation is what we want to do. So might as well actually look at the temperature as a departure from Tf rather than the actual value. Okay, so when you now talk about departures, then you start magnifying that value rather than look at high values and then varying over a small range there. So set a new variable sigma as Tf minus T, and then sigma I becomes Tf minus Ti, and of course sigma is now going to go to 0 when T becomes Tf. So sigma equal to Tf, right, and we also have to find out what T is like. So T is Tf minus sigma equal to Tf times 1 minus sigma divided by Tf, and we want to note that sigma divided by Tf is much less than 1, right. So sigma is a very small value, it's a departure from Tf. It's not going to be large because T itself is not going to, it's going to vary only from Ti onwards to Tf, and Ti is quite high, very close to Tf in the first place. So this difference is going to mean that sigma is going to be very small when compared to Tf. So then how is your e to the minus E over RUT going to get changed or transformed in terms of sigma is exponential minus E divided by RU Tf times 1 minus sigma divided by Tf. So that's approximately exponential minus E over RUTF times 1 plus sigma divided by Tf. Now these kinds of things are all sort of tailor made for approximations. We should sort of get an intuition about how these analyses are done. So if you now start thinking about a sigma as a small quantity, then that's like a sitting duck for a binomial approximation. Okay, so whenever we have a chance we approximate. Okay, we do that in our lives most of the time, by the way. So we do a binomial approximation, and then it also gives you this factor which we have a feel for from here, right. So we get all these things isolated, then I is equal to, you can pull out these things, Ti to Tf e to the minus capital E sigma divided by RU Tf squared dt, whereas our integral is with respect to sigma, So therefore we should write this as AE to the minus E over RUTF integral sigma I to 0 e to the minus E over E sigma TF squared d sigma. Now that's a little bit of a cumbersome thing over there. So what you could do is let not very cumbersome, it's possible to deal with this, but still if you want to now call this as E over E sigma over RUTF squared and beta I is E sigma I divided by RUTF squared, then I is AE to the minus E over RUTF squared divided by E, it's pulled out, and 0 to beta I e to the minus beta d beta. Now this is, so what are we expecting, what are we expecting to happen? What we are basically saying is that we are looking for this integral, which is what we started out with, to approximate W naught infinity divided by a different beta than what we have used here, unfortunately, okay, and that beta was E times TF minus T naught divided by RU TF squared. TF minus T naught is already here, so we should be looking for something like RU E divided by RUTF squared in the denominator to couple with this in order to get you the Zeldovich scaling factor, and then we should get a W naught infinity. W naught infinity is essentially the W evaluated at the reactant concentration levels and product temperature levels. We are now doing a 0th order reaction which does not depend, whose reaction rate does not depend on the reactant concentrations anyway, so we do not have to worry about the not part of the W naught infinity. We do not have to worry about evaluating it at the reactant temperatures. What we have to, reactant concentrations, what we have to be looking for is to evaluate it at the product temperatures, which is what this is. So this is the reaction rate expression evaluated at the product temperature, right, and then this is there coupled with the TF minus T naught in the denominator. You are going to get the Zeldovich scaling factor in the denominator. So this all by itself is giving you, for what we thought was the average reaction rate, giving you W naught infinity divided by beta. So we are fine. So all we need is a unity out of this integral. Sure enough, that is what we are expecting to get. So this is going to be like 1 minus e to the minus beta I, where we are now saying that beta I corresponds to sigma I, and sigma I corresponds to TF minus TI, which is a very small quantity, right, when compared to TF. Therefore we are now going to get rid of it and say this is approximately equal to 1, right. And then from there on we should now be saying therefore SL is equal to 1 over rho naught integral 2k divided by Cp AE to the minus E over RUTF, that is W naught infinity for a 0th order reaction, divided by TF minus T naught times RUTF squared divided by E. So E times TF minus T naught divided by RUTF squared is the Zeldovich scaling factor showing up the denominator of W naught infinity. So we essentially are getting back the same thing again except for the square root of 2 that's come out again, right. So this is typically how we are able to retrieve the answers that we were expecting for this case. What I want to point out, just point out, not really go through this because we are just spending too much time on this. You should look up, so this is looking like what we got before, right. You should look up how to actually do the rigorous analysis on taking into account the reactant concentrations. Then what that means is we have to now relax this assumption on a 0th order reaction, and notice that W will now depend on the reactant concentrations. So for a first order reaction you will have a concentration of one of the reactants coming into picture. For second order reaction you are going to have concentrations of 2 reactants coming into picture. So all those things have to be brought into account. And then the next thing that we talked about was the lowest number effect. Okay. So what you will find is you can actually when we did the lowest number, for example, we found that and also the reactant concentration, you got this W naught infinity divided by beta power m for the where m is the exponent corresponding to the order of the deficient reactant, right. And then you also had a lowest number in the numerator. So we should be able to retrieve those things if the 0th order reaction assumption is relaxed and non-unity lowest number of reactants considered, right, we can retrieve the expressions obtained earlier on a order of magnitude basis, here with a square root of 2 factor, right. So we can get this. And then what would we suppose then? So we notice that for, let's say for a nth order reaction, right, W goes as p to the n, right, because you will have the Arrhenius expression times the concentrations as many as the number of reactants are and the order the reaction depends on, and for that much order you are going to have each concentration contributing a pressure, and therefore you are going to have a p to the n for the nth order reaction for the pressure dependence, right. Now what you have is rho naught in the beginning, right. So rho or rho naught goes as P. I don't want to say P naught because we are assuming the pressure to be constant. It does not matter whether it is P naught or P infinity. Okay, we are just talking about a constant pressure, more or less a constant pressure deflagration here. Therefore your SL is going to go as P power n by 2 divided by P, n by 2 coming from having W depend as p to the n and then under square root. Therefore you are going to have this as p to the n minus 2 divided by 2, right, or you can say n by 2 minus 1, so n by n minus 2 divided by 2. So for a second order reaction, SL is nearly independent of pressure. Keep in mind, order is a global quantity. It's valid for a global reaction, right? Or if you're able to actually represent a scheme of chemical reaction steps, elementary reaction steps in terms of a global reaction, so it doesn't have to be an integer. So typically for most what we call a second order reactions, let's say hydrocarbon, gaseous hydrocarbon oxidation, your order of the reaction is going to be somewhat like, let's say 1.8, so it's not going to be exactly 2, right? So there's a reason why I'm saying nearly. So we find that there is a weak dependence on pressure. So if you now think about an n that is like about 1.8, you see you're going to have an inverse dependence on pressure, right? That means as the pressure increases the SL decreases, okay, that's in fact true, that's what we actually observe, but it's a weak dependence. So we are now beginning to talk about dependencies of S on various factors. So what we just mentioned was pressure, which was obvious. What we have not really worried about is how it depends on, let's say, initial temperatures, okay, and what we will see is this is primarily the dependence there, and SL is going to depend on a lot of other factors, mainly through W, okay. So if W is going to depend on initial temperature, it will depend through TF, okay. So we will now talk about these things in the next class.